This is another video on review of sequences in series needed for real analyses pertaining on the making of proof for limit theorems. We are going to prove here that the limit of the product of two sequences is just equal to the product of their individual limits. So we have this statement: let a sub n and b sub n be convergent sequences of real numbers, with the limit of a sub n being L sub 1 and the limit of b sub n is L sub 2. Then, the limit of their product, a sub n times b sub n, is equal to the product of their corresponding limits. To show the proof of this limit theorem, we're going to use the definition, which would entail us later on to identify the correct forms of our epsilon. As part of the proof, we're going to, number one, make sure that whatever expression we can come up later on, we can express them with the individual expressions of limits. Saying here, these are the connections. Make sure that they will appear, or the forms of their definitions as well will appear later on in our process of the proof. And then we can invoke forms for our these limits for representations with epsilon, so that later on we could come up with the final form of whatever the form with the epsilon itself. I'm talking about this one. So this is already the fourth video. In the first three videos, we already talked about the limit of the sum, the limit of difference, and the limit of the product of a constant and a certain sequence. So let's start with the proof here. So let epsilon be greater than 0. So it appeared here. What we need to do is we must show that there exists n, which is an integer, such that if n is greater than n, this is the definition, okay, that's a comma, then the limit, or now the definition itself, the absolute value of the product of a sub n and b sub n minus the product of their corresponding limits is less than epsilon. If we could show this, because this is per definition, then we can invoke that this is really true. So take note, this is our goal. Please be guided with that, because we need to make sure that we can have this form. So what we need to do here first is to try breaking this portion into forms where this will appear in terms of the definitions by each of them. So let me go to this one here, and please bear with me. Note that we have the product of a sub n and b sub n minus L sub 1 and L sub 2. Okay, let us try to add some 0 in the middle. Okay, a sub n, b sub n plus 0 minus L sub 1, L sub 2. Okay, I'm adding 0. Don't worry about that. It's the identity element for addition, so we are not changing the actual expression, but I'm adding 0 here to introduce inverses where I could use later on to be paired with this 2, so that they will come out later on. I'm talking about what are they? I'm talking about this a sub n minus L sub 1 for this, and b sub n minus L sub 2. This should come out in this form later. Okay, so that's why I'm introducing 0. Here is how it goes. I am introducing this minus a sub n L sub 2. Take note, they are not the same. Okay, but since I introduced that, I will make sure that I will neutralize that here. So these two are just equal to 0. Okay, that's the purpose of adding 0 there. Minus L sub 1 and L sub 2. Why am I doing this? Such that when you look into this one here, I have a common a sub n. I have a common L sub 2. Once I take it out, this 2 will surely appear. Let me change my pen color to black, and I'm gonna show that to you. Okay, so once I take out a sub n, what remains for the first 2 is b sub n minus L sub 2. Okay, take note, this is one of the goal here, this. Okay, so it already came out. Plus, once I take out L sub 2, you have a sub n minus L sub 1. Sorry, this is parenthesis, pardon with that. Okay, so b sub n minus L sub 2, a sub n minus L sub 1, they are both corresponding to this, so they now appeared. That's the purpose. That's your goal. Make sure that they will appear, so that you can now invoke some representations later on their equivalence, or probably a value greater than them using epsilon. Okay, now from this, before we can use triangle inequality, because they are yet to be broken down, let us use here the triangle inequality, which tells us that if we have an absolute value of the sum, okay, this is absolute value of the sum, we can break them out stating that the entire expression is just less than or equal to the sum of the individual absolute value notations. So you have here a sub n times b sub n minus L sub 2 plus, again, the sum of the individual absolute value notations. You have a sub n minus L sub 1. Okay, so now that we have these two, we can now show here use one of the properties of absolute value notation, where if we have the absolute value of the product, then we can now break them into this form, the product of their individual absolute value notations. Okay, so this is just equal to that. Okay, that's one of the properties of absolute value. Also true here. And then you have a sub n minus L sub 1. Truly, these two came out. Not just part of the absolute value, but their individual absolute value themselves. Okay, so now that we are done with that, we can now go into representations. Okay, so take note, this we have here arbitrary, not arbitrary values, we have the values, absolute value of a sub n and L sub 2. Let us try to represent them with a singular or variable so that we can look into the properties later on as well. So how should it go? According to one theorem, okay, according to one theorem, we're talking about this one here. This is a absolute value of a sequence. Now, for an absolute value of a sequence, according to one theorem, it's always bounded. So there exists, according to one theorem, there exists, let's say m sub 1 greater than 0, such that the absolute value of a sub n is less than or equal that m sub 1 for all n integer. Okay, so once we were able to establish that m sub 1 where is just any value, not necessarily a sequence, now we can now invoke, or we set a certain constant m be the maximum of m sub 1 or the absolute value of L sub 2. So whoever would be larger to them, we are going to use m to represent them. Why? So that these two forms will be represented by a singular variable m. Okay, so we can say here, hence, okay, we have the absolute value of a sub n is less than or equal to m, because whichever will be the maximum, and the absolute value of L sub 2 is also less than or equal to m, whichever would be the maximum to them. Maximum to these two, they would be greater than or equal to this both expression, because we would like to have this form. Thus, since we can have this expression, this form earlier, this form, okay, I'm talking about this form, we will have here a sub n times b sub n minus L sub 1 L sub 2, which is equal to, not equal necessarily, sorry, which is less than or equal to this entire form. Okay, a sub n, you have b sub n minus L sub 2 plus L sub 2, absolute value of that, and a sub n minus L sub 1. According to the triangle inequality, this is still less than or equal to m. Now substituting this to our a sub, absolute value of a sub n and L sub 2, b sub n minus L sub 2 plus another m, a sub 1 minus L sub 1. Why are we doing this? So that we can now proceed to setting the appropriate expression for epsilon. So going here, since the limit of a sub n is equal to L sub 1, then there exists n sub 1 element of z plus or set of positive integers. Now, take note, this is similar to what has happened to the previous first two videos on the sum and difference of our limits, because we have two limits here. So, such that if n is greater than that n sub 1, then you have a sub n minus L sub 1 is greater than epsilon over 2. That's what we used last time. Okay? Not epsilon, but epsilon over 2 because we have 2 of them here. But take note, we have constant m here. How do we make sure that this, when combined to m, will return to a certain epsilon, noting that there are 2 of them? Okay? Because if this is just epsilon over 2, once you substitute here, m will still appear. So what you need to do here is epsilon over m. But make sure that there are 2 of them, so there would be also a factor of 2. That is why, for the final form, this is where it gets tricky. This is where your knowledge of making sure that we can have an epsilon control is very important. Let's introduce twice m. You will see the beauty of this later on once we combine them to the final expression. And then also, the limit of b sub n, which is L sub 2, then there exists another n sub 2, element of z plus, such that if n is greater than n sub 2, then b sub n minus L sub 2 is greater than epsilon over twice m as well. So we have twice m and twice m here to be combined to this. Okay? But of course, we're going to assume that into one variable. Please bear with me as I will add another page. Please bear with me as I will add another page here. Okay, because I don't have much enough spaces. So let me copy these portions. Hopefully I could copy all the important concepts. Okay, let me copy that, move to the next page, and then paste it here. Okay, I believe all the important parts are recorded here. Okay, so what we need to do is to make sure, okay, take note, let me return to the previous page. This is our goal. Make sure that we will have this form here, be less than epsilon. That's our goal, to invoke that this is true. Okay, this was actually that form. Okay, less than to this. Okay, so we are having all the necessary details here. So once we have n sub 1 and n sub 2, let's make them into 1 because we only need to have one n. Okay, so let's have here, take n be the maximum of n sub 1 and n sub 2. We need this because whichever is larger and we take the maximum of the two, it still follows the idea of n is greater than n because n will still be greater than this, which is the maximum of both. So it's still okay. Okay? So once we take that, let's have here, if n is greater or equal to n, okay, sorry, this is greater than equal, rather. So greater than or equal to n. Okay, so we now have, then, let's write this form. The absolute value of a sub n, b sub n minus the product of L sub 1 and L sub 2, which was broken down into this. Again, the m resulted from the previous discussions in the previous page. You have here, okay, as we have this theorem and then letting that m greater than the absolute value of the sequence a sub n and the limit L sub 2, or greater than or equal to that. Okay, so you will have here greater than or equal, or less than or equal rather to this, m, the absolute value of b sub n minus L sub 2, plus m, the absolute value of a sub n minus L sub 1 here, this one here. Okay, but since this has been declared as less than epsilon over twice m, and this is also the same, this is why I told you earlier this is correct, and this is very important to come up with the correct expression, because you will have this form. This is still less than, okay, m, and this expression is epsilon over twice m, plus m, epsilon over twice m. Okay, we have these two here. Now, looking into this is equal. Okay, take note, don't be confused with the notations. Take note, when once you have this, it will be cancelled out, and cancelled out, you will have epsilon over 2 plus epsilon over 2, which gives us, let me remove the cancellation. epsilon. This is now our goal. That's why we have epsilon here. Because if you're going to return here and say for example, you just simply use epsilon over 2. Okay, what if it's just epsilon over 2 and epsilon over 2 here? So you will have here epsilon over 2. Let me remove epsilon over 2 and epsilon over 2 here. You will have the form equal to epsilon times m, right? Because you will have twice m. This is what will happen. You will have twice m epsilon over 2. So you will have epsilon m or m epsilon. This is not the goal. The goal here is just epsilon. That is why it's incorrect. Okay? So it's incorrect. It's correct here. If you also use epsilon over m, if you use epsilon over m here, sorry for making this video longer. So you have epsilon over m, this is m, sorry. This is epsilon over m here as well. You will see that this will be cancelled out, but you will have twice epsilon. What we really need is just epsilon. That is why it's very clear, hopefully it's now clear, that the correct form of your epsilon here must be epsilon over twice m. So that you have m, epsilon twice m twice m, cancel the m, epsilon over 2 plus epsilon over 2 is just epsilon. Okay? So hopefully that's okay with you. And then finally, this gives us just this form. The absolute value of a sub n, b sub n minus l sub 1, l sub 2 is less than epsilon. This is what we would like to show. That's why this is very important for you to be guided. For there exists n. Okay? There exists n. That's why we use here n alone for the maximum of n sub 1 and n sub 2. So basically, once we have that, we will have our conclusion. Since epsilon is greater than 2 is arbitrary, then we conclude that the limit of the product of two sequences is just equal to the product of their limits. This is the end of the proof. Pardon for making this video very long because you really need all those inputs as you will construct proof like this if you are required to do so. So make sure that you will do the same, or you can make this even shorter if you would like to, but don't forget the important details such as this theorem for bounded convergent sequence. You will have this form, and of course triangle inequality, and then the one of the property for the product of absolute value, where you can simply break them into this part. I'm talking about this portion here. Okay? Thank you very much for watching.